Homework 0 is essentially all review stuff. Should be for most people. Homework 1 is a mixture of some things which are review and some things which will be new for most, if not all of you. Just keep that in mind. So to understand what's going on in homework 1, this lecture is pretty important. We'll be introducing some ideas and ways of thinking that are kind of featured heavily in homework 1. The discussion tomorrow and the little bit of discussion we have on Wednesday, that will also help you kind of understand the material we talked about in lecture today and get ready for what you need to do for the homework. So, do you remember last time we introduced these ReLU networks, with a single, fully connected layer, and we said, okay, let's build this thing up to understand piecewise linear functions, right, as a universal approximator, from the traditional perspective of, hey, what do we need from a model that we want to fit to data? We have to be able to express the patterns of interest. So one of the ways of thinking about it is, can you express all patterns? And piecewise linear is kind of an approximation to all functions, so great. And one of the things that we commented on at the end was, if you looked at the parameterization we had, I'm not going to write it up again, maybe I'll get to it near the end of the class, but if you look at the parameterization we had a set of weights at the beginning, and then we had another set of weights after the first hidden layer. And we saw that in terms of what is being expressed, those two weights are kind of not actually redundant, but they're sort of redundant, right? That both of them adjust the slope of the line, of the line segment, if you remember that. So this issue of, you should be, in the back of your mind, you should be thinking of, well, okay, in general, when you're going to parameterize a network, you might get these kinds of little bits of redundancy. How does that show up in terms of what you actually learn? How does that influence learning? Because again, if you remember from last time, we talked about how what really defines the current age of deep learning, the kind of advance, was the withdrawal of focus from being able to approximate all functions and starting to think about, well, does this network trained on actual data using the learning algorithms, the training algorithms that we have, does it actually learn patterns of interest? Right? So can it actually learn the thing that you care about? And so what we're going to be talking about today is we're going to start introducing some tools and some ways of thinking that are building towards an understanding of what actually about an architecture in the context of things like gradient descent, what actually makes it favor certain kinds of things in terms of what it actually learns. Okay? So that's the topic of today. So if we think about it, what we're going to do is we're going to use regularization as the way to understand that. Because regularization is you add a penalty term, the traditional approach. You add a penalty term, and the goal of the penalty term is pragmatically, I didn't use the penalty term. It learned some gibberish or something I didn't like, or I think something I'd make better. So I'm going to add a penalty term to shape the optimization so it learns something more to my liking. Right? The pragmatic view of regularization. Make it work better on the kinds of problems that I actually have. So let's think about, so what regularization is doing is shaping what does something actually learn. So first thing, I want to make sure everyone understands this. Everyone understands how adding an explicit regularizer, a cost term in the optimization, doesn't change the expressive power of your network. Does everyone understand this? Okay, it's really important. It doesn't change. Whatever functions you could represent before, you can still represent them. All you're changing is how what the optimization is favoring. Okay? So that's why we're going to use regularization to kind of try to get at this concept. So let's think about it. We have a loss function for your parameters theta, which is we wrote this last time. It's the sum over all the training data, some training loss, some label associated with the ith data point, and your parametric function that you're learning f theta evaluated at the training input xi. So this is the standard loss without the regularizer, and you can add to all of this a regularizer if you want. So to understand all these things, it's all very general and abstract and hard to wrap your head around. It's really important that you understand at least one such model well at an intuitive level. And the standard one we're going to use, because it's the one we understand the best, is, least squares with ridge regularization. I'll put paradigmatic. In large part because it's the only one we understand that well, is least squares with ridge. So what's least squares with ridge? Least squares, the problem looks like this. I have some matrix X, I have some weights W that I want to learn, and I want to approximately have this equal to a set of labels Y. So remember, think of this as a big matrix. N rows corresponding to the n data points. D columns corresponding to the features in your training data. This is a d-dimensional vector, because you have to learn weights for all of the features. And this is a column that has n labels in it for the n data points. Okay? So least squares means I want to approximately solve this equation. Like I want to understand what are the weights that generate those y's, which I do by optimizing the cost with ridge, right? Optimize cost. And I'm going to drop a 1 over n just for not having to track that thing. I'll bring it back when I need it for when it's important, but right now I'm going to just for simplicity eliminate it. So I look at the error of my prediction squared. So this is an n vector. I look at its length squared, usual 2 norm. And I have a penalty term that says, please don't make these weights get too big. Also 2 norm. So far, should be completely familiar to everybody. And this has the solution in closed form. Which is, I'll write it in its classic form, x transpose x plus lambda times the identity inverse x transpose y. So just to understand this matrix that we're inverting here, this is a d by d matrix. Is this good for everyone? Good. So we're going to make sure we understand this better, and we're going to understand this in some different ways. Those ways are represented on the homework. So everything I'm going to do kind of fast in lecture, you will have to do kind of dotting the I's and crossing the T's in the homework to make sure that you understand it. But let's make sure that everyone understands this, the basic story, what's going on. Okay, so to understand what's going on here, let's first, there's like different perspectives we can take to understand what's going on. I'm going to start with just how does gradient descent work on this? Okay, because we're going to use gradient descent as our optimizer. So let's think about, this is the closed form solution. Great, one shot, you get this. How would gradient descent solve this problem? So first, let's think about just for straight ordinary least squares. Consider this the OLS loss. This is the ridge term for us, right? Let's just break it up into two terms. So let's start with for OLS. How far do we move? Right, so what's the gradient? So again, this is a straightforward calculation. We move eta. So I didn't put a 1/2. Sometimes we put a 1/2 here. So I didn't put a 1/2, so I'm going to keep the 2 when you take the gradient. 2 eta x transpose y minus xw. So whatever the iterate is. So the tth iterate. That's the move we do from gradient descent, right? How do you do that? Again, this is, you've already been playing around with this stuff in the homework. You take this thing, you can take its gradient, you write it out as a quadratic form, take the derivative, this will pop out. But it's good to understand what it means, just so we're all on the same page. This is the residual, right? This is how much is left. Like we have a current way of doing the prediction that gets us this. We want to get all the way to y. We aren't there, so there's something left. This is the residual. And this is like an adjustment, a bending of the residual to go in the right direction. Any questions on this? Make sure everyone's on the same page. All should be review. Now, let's do it for ridge. So ridge is going to have, if you look at this loss, we have the same loss we had before, except we added another term. So we're going to move in this direction with another thing. Is that clear to everybody? Right, just linearity of derivatives. So you're going to have, so I'm just going to group the terms together. I'll pull the eta out because I don't have it. Yeah. I guess I can pull the 2 eta out. 2 eta. And now I'll get this guy. Which is the contribution of the residual. And I'll get from the derivative of this. So what do I get from the derivative of this? I'll get minus lambda Wt. Okay? So I want to make a comment here on this thing, just because it's a bunch of stuff to review, so we might as well get this comment done right here. If you look at this, this is the kind of how you move, right? So you have two things you move. You move in the direction here of the gradient, kind of negative gradient, move this direction. And then you have this other thing, which basically, how do we interpret this thing? What this thing says is, hey, you know what? however you are, whatever direction you're pointing in currently, like move closer to the origin. Right? Like come in. Does everyone see that? So let's think about it actually iterate, right? So let's look at the iteration. So for this one, let's write it as the iteration. So WT plus 1. The next weight, I'm going to take this term. So what is WT plus 1? WT plus 1 is the old WT plus the thing that comes from the gradient descent, right? But now there's a WT sitting here with a minus lambda there. So I can pull that term over. 1 minus 2 eta lambda. And then here I get the gradient term that's just the OLS standard gradient term. Okay, this is like a comment on how gradient descent works for the context of ridge. Is that clear to everybody, what I did? If it's not, ask. Just algebra, but I'm skipping steps. Yeah?
You said moving closer to the origin. Are we adding the ridge term, the regularization term, or are we subtracting?
Okay. So what I'm writing here is the direction we're moving. Okay? It's not the gradient. The direction we're moving is what I'm writing. Okay, so this is the negative gradient. So if you look at the negative gradient for ridge, you have a minus lambda w. So when you combine that with the full iteration, that you get a 2 eta, because I didn't have the 1/2, right? 2 eta lambda. And instead of just having the WT from last time, you have 1 minus 2 eta lambda. So you should think about when the learning rate is small enough, right? And the regularization term is small enough, which it better be for things to work well. This thing here, this is basically bringing the weight, it's a stable thing pulling the weight in. Do you see that? It's like pulling the weight towards the origin. So if you didn't have any more stuff coming from this, okay, what this would do, if this was 0, this would, as time iterates, would make the weights decay to 0 exponentially fast, taken as a geometric. Did everyone see that? So this term is called weight decay. So in deep learning context, sometimes you'll see as an instead of talking about things in terms of, oh, I have a ridge term or something like that, they'll say, I'm going to use this optimizer, and I'll have this for my weight decay parameter. And what they're talking about is basically controlling this thing in the optimization. Okay, so it's an important piece of terminology you should know. Connect to something. It's not mysterious in any way. It's just something which comes out of very naturally inspired by gradient descent for ridge. Okay? Yeah. Yeah, it's a good question, right? So if you make your lambda become too big relative to your learning rate, right, it's kind of interesting, right? Because if you think about it, when lambda is really big, you're saying, please, please make these weights really small, right? But just grinding through the math, right, you see that, well, there might be a negative interaction with the learning rate if the learning rate is too big with a lambda that's too large in the context of weight decay. I mean, if this is where you're coming from. In many libraries, you actually have direct control over this term. But as a comment, many people have gotten confused about why something is working the way it is in practice because what they've done is they've added a regularizer explicitly that's a ridge type to their loss, and also enabled weight decay. And sometimes on the computer, you can get it to say, to have more of this effect than you might have intended, because you've got to ask for it twice. So it's important to keep this straight. And one of the interesting things we'll talk about later, when we start talking in the direction of transformers, is we'll talk about optimizers that try to be careful about how they're doing this effect. Okay, but this is just a bit of excuse to review and to bring this up as a piece of notation. Okay, so this is one perspective that we can have on just classic ridge. I want to do another perspective because we're going to use this all the time as a way of thinking. And in your machine learning class, this may or may not have been brought up. So I want to make sure everyone is on the same page with this. So whenever you see a problem that is largely defined using Euclidean norms, two norms, and linear algebraic things that are going on, then one tool, very powerful tool in your arsenal, is to say, can I understand better what's going on by looking in some different coordinate system? This is always a good idea, generally. But in the case of two norms, you have a rich arsenal of ways of getting coordinate systems. So it's always good to see, can I understand what's happening in a different coordinate system to see more clearly what's going on? So in two norm, your go-to tool is the SVD. And we have homework to make sure you review this. Okay, so the singular value decomposition is super useful. So what we're going to do is we're going to look at what we're doing here, and we're going to look at it with the lens of the SVD. So here, there's a perspective that's important to keep in mind. What we're going to be doing is taking the perspective of an outside observer. Nothing we're doing is going to be impacting what the algorithm is doing or anything. We're just going to look at it from the perspective of an outside observer, watching what's happening, who has access to the SVD. So the outside observer has the SVD. So the outside observer says, hey, you know what? I know that X, this n rows d columns matrix, is actually equal to U sigma V transpose, SVD. So again, let's make sure we understand the types of everything. What size is, so X, remember I'll label it right here, X, N, D. And so for our purposes, we're going to use the full SVD. Because it'll help us keep some things more straight. So in the full SVD, what is the size of U? How big is U? Someone just raise your hand and shout it out, or just shout it out. N by N, right, yeah, exactly. This is N by N. What's the size of V transpose? D by D. And what's the size and shape of sigma? How many columns? D columns, right? And n rows. Same shape as X in the full SVD. So we do this. And now remember, SVD has a cool property that these guys are unitary, right? Orthonormal columns, sometimes called orthogonal matrices also. Unitary is used when you might have complex. And rows So they're really useful because they represent coordinate systems that are like rotations that don't change any angles or any lengths. So if what you're talking about doesn't care about rotations, rotation type things, or rotation reflection type things, you're free to switch to those coordinate systems and nothing will change. So that's really cool because here you have two norms. This is a two norm on what size vector? Right? An n-dimensional vector. And this is a two norm on a d-dimensional vector. Both of these, will play nicely with this. So if you use the SVD to understand what's going on a little bit better, then what happens? So we have many different ways of doing this. I will take a particular perspective that's going to be like in shorthand. So I take the problem that I have, right, in terms of what's approximately equal to what. So I can see, what's going on as I change coordinates. So I take this perspective and I say, okay, so I have U sigma V transpose W is approximately equal to Y. This is the same problem because I'm looking, when I say approximately equal to, I mean, hey, in two norm, the difference should be, good. So I can rotate everything. And it's the same problem, right? So I can take this and I can say, hey, I can change coordinates on W to be such that I look at a new W, which is V transpose W. And that's fine because all I care about is penalizing its length, and this doesn't change its length. So this is also cool. So I do this, and then I get sigma W transpose. And hey, you know what? This is just a Y. This is a rotation of the Y. I'll just call this a new Y. Y tilde. And now I have the approximate problem, which is sigma W tilde is approximately equal to Y. But this is a really nice problem, right? Because let me expand out sigma. Let's think of the situation in which, for now, for illustration purposes, let's think of n as being bigger than d. So I can draw things in some right shape, right? So this is going to be matrix like that. Okay? So now I can ask, what are the W's I'm going to get? Okay, so for the case, so now it depends on how I solve this problem. If I solve this problem using OLS, right, in which I'm not going to have a ridge term, a penalty term at all. So the OLS solution is just going to say, I'm going to use Python indexing. So look at the ith component of W tilde. This is just going to be 1 over sigma I for the ith component of Y tilde. If I is less than or equal to n and 0 otherwise. Did everyone see that? Important to understand. Now, so here I'm going to pause to survey the audience. For how many people is looking at OLS through SVD coordinates something that you have seen before? If you've seen it before, raise your hand. It's okay to raise your hand if you've seen it before. Yeah. Okay, if you haven't seen this before, raise your hand. Okay, it's like a little over half haven't seen it. So it's super useful and cool to think of it this way. Because what happened at a high level is by looking at things in SVD coordinates, what was a complicated vector problem has essentially decomposed into a sequence of scalar problems, right? And each of these scalar problems is easy to understand what's going on. Okay? So this is very useful because complicated what's happening in some vectors, how things might be rotating or moving around, you can't wrap your head around. I mean, yeah. So I'm looking at the case where, okay, when I said I less than equal to n, by n I meant like however many of these are not 0. The instant you get zeros, it's just, you say 0. Because think about it. If you have a 0, what's going to happen? You have a row that says 0 times a bunch of stuff is approximately equal to something. Please adjust the stuff. You're like, well, I can't. Right? There's nothing I can do about that stuff. So, right, it's like it's not there.
For the purposes of this problem, you said that n was like greater than d. So what is like d be the max value for n?
So if n is bigger, then it's a tall matrix. And so the sigmas run down the diagonal. And so you'll run out of places to go before you run out of rows. Hence this shape. Does that answer your question?
Yeah, okay. I wasn't sure if that n was referring to like the original n or like smaller version of n.
N here refers to the original problem. How many data points do I have? Okay? So this is the OLS solution. What's the ridge solution? So for this, it's useful. I'm going to talk fast. You need to work this out for yourself if this is not clear to you. Okay? So for ridge, you have an optimization that looks like this. Okay? Which means after you have made this change of coordinates, you have an optimization where everything that is replaced in the following way. For ridge, this becomes y becomes a y tilde, x becomes a sigma, w becomes a w tilde. Okay? Right? This is your optimization problem. Every time you have a Euclidean norm squared, it's just a sum. Does everyone see that? It's just a sum. So this is just a bunch of sums. Now, let's think about it. You want to minimize this. You're penalizing the length of w tilde. Are you going to change this part at all? No, obviously not, right? These w's out here are doing no work for you at all. They don't help you reduce your residual in any way. And they cost you length, right? So you're not going to set them to anything other than 0. So this part is just unchanged. Okay? Now you have n terms in which you have n different optimization problems that are just summed up. So you might as well consider them n decoupled optimization problems. Like there's no interaction between them. Okay? Because this is diagonal. So it's like solving a scalar ridge problem. Because you're solving a scalar ridge problem, the solution, you can just grind out the algebra. It looks like this. Let's write out the answer. So this is just like scalar optimization. Right? Gives you this. So this is, so again, you can see it here. Okay, so maybe this is a good, if you haven't done this before, I strongly encourage you to do this exercise. In the interest of time, I don't want to do it because I have more things I want to talk about. But remember, we said the entire problem just transformed to having a sigma anywhere you had an x, a w tilde anywhere you had a w, and a y tilde anywhere you had a y. So this optimization answer also transforms in the same way. W tilde equals sigma transpose sigma plus lambda times the identity inverse sigma transpose y tilde. Right? I'm just reading off the transformation. Sigma transpose sigma is just a diagonal matrix filled with sigma I squareds. Plus lambda times the identity is plus lambda. Inverse of a diagonal matrix is a diagonal matrix with the reciprocals all the way down. Sigma transpose is just going to pick out sigma I times yi tilde. Right? So you can also do it just by formula. It's good to be able to go back and forth between these different perspectives. Yeah?
I'm not sure if I am confused or not, but the sigma large matrix, if you see the entries of the sigma large matrix, the last term should be sigma d.
Okay, so this is shorthand. Okay? Oh, so you're right. Sorry. My mistake. Sorry. Thank you. You attempted to point it out before. I did not catch it when you did. Sorry. Is that way if you have this is what it looks like if n is less than d, then it looks like this. If n is greater than d, then it looks like this. Oh, sigma d. You're right. Thank you. Yeah. So one of these two. So I was talking about this case. So this is not n, but d. Thank you for correcting me. Good. Sorry. Everyone understand what's going on? Yeah.
But in that case, W is a vector in RD.
Yeah.
Otherwise.
Oh yeah. There's no otherwise case. You're right. This case doesn't happen. Yeah. Thank you. I'm just doing this so that you can understand. The reason I'm writing it this way is I really also very much care about the case, which is this case. So I want to acknowledge the otherwise case, just get it on the board. Thanks. Okay, so the SVD perspective is interesting and nice. So I want to dwell a little bit about what's happening here. Okay? So let's write out this aside. Yeah. Sorry? Sorry. Let me just write it this way. I'll write it correctly. There you go. Okay? Or basically, yeah, it's the idea here is that your training data is some dimensional. Okay? So whatever that dimensionality is going to cause you to have some number of singular values. So whatever that number is this, right? That we care about here. Okay? So it's important to understand what this is doing, right? Now, if you look at it this way, right, a perspective on just this closed form solution says, look, if x transpose x is too close to being invertible, not invertible, this is close to a singular matrix, then inverting it would be bad. Adding a lambda I pushes it away from being singular and prevents this from causing giant things to happen. That's kind of at the high level of looking at the level of matrices. But when you look at it at this kind of more refined level, you can actually understand this object better, right? So you use the classic kind of analysis that one does, for example, in analyzing Bode plots in circuits for responses, where you say, look, lambda is going to be something different than sigma I squared. It's either going to be intuitively much smaller than sigma I squared or much bigger than sigma I squared. So let's understand what happens in those two regimes. Okay? So this thing, so make an aside here, right? If you add two numbers together and one of them is much bigger than the other, how does addition behave? Right? Think about it. You take two numbers and you add them. What is 1 billion plus 0.02? A billion, right? Right? When you take two numbers and they're very different in size and you add them, the bigger one survives and the other one's gone. Right? This is like just how addition works. So if lambda is much bigger than sigma I squared, right? Then this thing is approximately equal to sigma I divided by lambda, if lambda is much bigger than sigma I squared. Alternatively, you can think of it as if lambda is much bigger than sigma I squared, then lambda divided by sigma I is much bigger than sigma I. You can think of it that way too. Either way, you get this. If, on the other hand, lambda is much smaller than sigma I squared, then this sum is basically just sigma I squared. And in that case, sigma I squared will cancel with the sigma I, and you'll just get a 1 over sigma I if lambda is much smaller than sigma I squared, and smoothly going in between. So looking back here, what it says is ridge regression for those directions that are well represented in the training data, meaning what? Meaning that their singular value that you have is substantially large relative to the ridge regularizing parameter lambda. For those directions, effectively you get the OLS solution. So if a direction is well represented in the training data, so for those who come from a background in controller system ID, if the input, the training data is sufficiently exciting those modes, the regularization will do nothing. It'll just allow it to preserve straight through. Yeah?
What's the practical difference between using a regularizing parameter and removing the vectors in our data set that have like the smallest sigma value?
Okay, good. That is an excellent question. I will repeat it with a twist to make it parse a little bit better. So the question is, hey, look, if I look at this interpretation of what's going on with the ridge regularization, what it's saying is that I'm going to set those weights to be in the transform. Remember, this is all happening from the perspective of the observer, right? Gradient descent is just grinding away, doing its thing. It can't see this. The observer outside says, I'm looking at this matrix in the right coordinate system. I'm going to look at what's happening in this other coordinate system. So from that other coordinate system's perspective, the observer's perspective, that outside observer is saying, look, ridge is going to basically set some of the weights in the transform coordinates to what they would have been for ordinary least squares, and is going to put others close to 0. Right? Because lambda is much bigger. So those are going to shrunk down to 0. By contrast, those weights, if for example sigma I was tiny, OLS would be blowing them up. So everywhere OLS would be blowing those weights up to be big giant numbers, with an appropriate lambda, ridge is going to set them closer to 0. Okay? This is the perspective of the outside observer. And there's some smooth thing happening in between, okay, for the intermediate weights that are close to, whose sigma squared is close to lambda. Now, to continue answering your question, in practice, it has been found in many, many, many kinds of applications that when you have natural data of any kind giving you some kind of matrix of features or data, that those things tend to have a wide dynamic range of singular values, right? That you don't tend to have singular values that are all kind of hanging around in one place. You tend to have in many problems, you tend to have a wide dynamic range of singular values. So this becomes useful in dealing with this wide dynamic range of singular values. Okay, now, you could say, to rephrase your question, you could say, if that's the perspective of the outside observer, why can't we take advantage of that outside observer perspective algorithmically? And algorithmically say, for example, let me take the SVD explicitly, algorithmically, before I tried solving anything. And let me use the SVD to do dimensionality reduction, where I will dimensionality reduce by projecting my data into a low-dimensional space, precisely that low-dimensional space, which corresponds to the high singular values in X. So I only take those directions where you actually have sufficient representation of signal in the input to actually excite any mode of a linear model. And I'll only fit that. That's explicit dimensionality reduction by using the SVD. What this is saying is that, in fact, the two solutions will behave somewhat close to each other. But here, for ridge, you never had to take an SVD to get that benefit. No computational cost was required to compute an SVD of a giant thing. It wasn't needed. What happens is it just happens for you automatically by doing gradient descent with weight decay. You're already getting that benefit. Okay? So algorithmically, in terms of practice, it's important to know when you need to do something and when you don't need to do it. So it's kind of interesting that way, that you might have started off saying, look, I better do dimensionality reduction. And you say, well, let me first just try ridge. And ridge just worked. It's like, oh, that was cool, right? You can save some work in terms of doing it. But yeah, it's good to, sometimes explicitly in deep learning, we will do things that are counterparts of dimensionality reduction followed by, fitting. But here, I'm just trying to show you, you don't necessarily have to do that. Yeah.
So, ridge is still keeping all the features, right? Dimensionality reduction, lowers it. Does that affect the activity of the model at all? Or is it regular as well?
Okay, great. So this is now you're getting into where we want to be, right? So the question is, has any of my commentary changed the expressivity of the model? Okay, and the model is still what the model was, right? So in our case, that we have a linear model which says you're allowed to use any linear combination of the features that you see, right? The features might be nonlinear or whatever. There's some features, right? Any linear combination of them is fair for you to use. That's the expressivity of the model. However, what this is saying is, sure, your model has that expressivity, right? You could do that. But if you choose to fit the data using gradient descent with a weight decay term, you're not actually going to use that full expressivity. If there are dimensions which are not well represented in the training data, you're not going to set them to anything. And you're basically going to take the default. Whatever the default is. In this case, it's a linear model, default is 0. In other models, the default might not be 0. You'll get whatever the default is in terms of how you predict along variations in that direction. Is that clear? Yeah, in the back.
So if we take the SVD, we actually get slightly more accurate results in some cases.
Good question. The question is, if you did explicit dimensionality reduction versus doing this soft one using ridge, which gives you more accurate results? The answer is you can construct examples that go either way. But the point is they'll be close to each other. They're not going to be hugely different. Yeah, question in the front.
Could you explain a bit more how the interpret going from 1 over lambda to sigma over lambda?
Great. Yes. How can you interpret this result? So we interpret it this way. So interpreting this, I'll just move this over. It's fine. Everyone remembers what's on that board. Okay. So I'm going to draw some functions. You should think about this axis as being on a log scale. Okay. I drew two functions there. Okay? One was a step that went straight and then stepped down and went somewhere. And the other is like a smoothed version of the step. You see that, these two functions? So what this is saying, when I talk about this difference, whenever you say something is much bigger than or much smaller than in terms of addition, you should think of that as being bigger and smaller on log scale. Because log is like order of magnitude scale. So when I said, think of a billion plus 0.2, right? These two are numbers that are different on a log scale. So what it's saying is that this function is this smooth one, is behaving roughly like this step, right? When viewed on a log scale. So it's going to keep for this, and this is determined by log scale sigma I squared, and this is lambda. It's like selecting which are the singular values which are going to get to contribute to the learned parameter weights and which are the ones that are not. Does that help you understand what I'm saying in terms of what this means?
Is it the log scale of sigma I?
Yeah, log scale sigma I squared, same as log scale sigma. Log doesn't matter if I square. Yeah.
Why do not? What if we use 1 or 0 norm? Will the result be similar or different?
Okay, great question. So the question is, I'm talking about everything in the context of 2 norm. What if we were thinking about 1 norm or 0 norm or 4th norm or something like that? Would the results be different? So remember what I said about the joke about the drunk man looking for his keys at the very beginning. We understand the geometry in 2 norm much better, linear algebraically, so we're going to use that to build our basic understanding. One hopes and believes that there should be parallel stories that occur for other norms. 1 norm has some other interesting things, and 0 norm has other interesting things that it does that aren't captured by what's happening in 2 norm. It is people's belief that if you look at some other norms, similar type stories should be happening, but we don't fully understand that, and it certainly wouldn't be as easy to understand and describe as here. But the key thing is that to understand how regularization is functioning. What I'm trying to help you understand here is that you can think about regularization as, you can think about deep learning as cooking, right? And you can think about, you have no understanding of cooking. You just have a set of spices and things that you add, okay? And you're like, it doesn't taste good, right? Let me look on the internet. It says add, I don't understand what this thing is. Okay, I'll take some and add it, okay? And I have no idea why I'm adding this, right? I don't even know what this thing is really, except that, some parameter in Python, right? And I don't know how much of it to add or what it means to add more of it or less of it, right? this teaspoon, tablespoon. If any of you cooked like and mistaken like a teaspoon for a tablespoon, you know, like this can happen if you don't know what you're doing, right? And sure, you can approach things that way. And sometimes you'll find yourself having no choice but to approach things that way. But what I'm trying to do is to give, for some of the cases, a little bit of intuition for what might actually be happening that you can understand. And then you're going to try to take that intuition to other domains. And sometimes it'll carry over successfully, and sometimes it won't. Sometimes we understand how to mathematically make that shift, and sometimes we don't. For those who want to understand these things, a very powerful set of tools for which, kind of build on your optimization understanding is to say, look, we're talking about gradient descent in 2-norm and doing things this way. If you want to go to other norms and try to understand what's happening, there's like techniques called mirror descent and so on that try to bring some of the geometric ideas over into other norms. But again, for deep learning practice, that tends not to be that important. So we're going to stick to 2-norm style intuitions. It's a good question, though. Great question. Okay, so you understand now what's happening. So behind this thing, we had gradient descent written out, which I should bring back. Okay? And we described as one perspective is look at gradient descent. Another perspective is look at things in terms of the SVD. You can combine these perspectives and look at gradient descent in terms of the SVD. And if you do that, you'll notice something. What's the transformation, right? Wherever you have an X, it becomes a sigma matrix. Y becomes a Y tilde. X becomes a sigma. This becomes a W tilde. Again, remember, this is the perspective of the observer. So let's write this out, just this term out. I'll write it here, in just a little section which I have some space, just to keep everything in one place before I shift to something different. So I'm going to write this out after this transformation, okay? That's the only key term that matters. 2 eta sigma transpose Y tilde minus sigma W tilde T. Right? So when you look at it at first, it just seems like, okay, how is that any more insightful than what you're seeing here? Right? It just, this is some matrix. But remember, these are diagonal matrices. Okay? So this is a diagonal matrix. This is a diagonal matrix. So you see something else interesting happening, which is that gradient descent in SVD coordinates is just operating coordinate by coordinate. There's no interaction between these coordinates at all. Just like the optimization problem decoupled into a bunch of separate optimization problems, even gradient descent in SVD coordinates is just moving along these individual coordinates by themselves. There's no interactions. Does everyone see that? So what's happening is that, look at this sigma transpose out here. This is saying, so let's look at it in terms of the ith coordinate, okay? So the ith coordinate is moving like this, 2 eta sigma I Y tilde I minus sigma I W T I. So that's what's happening. So what's happening is that for those sigma i's, that are big in your data, you're going to move more. Do you see that? This is like an important point we're going to build on. Okay, this is your step that you take in the gradient descent. So remember, you have two parts. You have a weight decay part. The weight decay part doesn't care about what the sigmas are. Did everyone see that? Just 1 minus 2 eta lambda, like whatever, right? Has to do with the lambda. It's how fast, lambda is basically telling how fast am I going to try to bring these weights to zero, collapse them to zero. It's like the gravitational pull of zero is what this is doing, okay? This is this thing trying to get to be a good fit. For getting to be a good fit, what's happening is it's going to move more in directions with large sigma. Directions with small sigma move very little because they get multiplied by these sigmas times sigma squared. Which you kind of expect to see here, right? The final solution basically doesn't go very far in directions which have small sigmas. But here you can see it kind of in the dynamics itself. The dynamics move in directions of large sigma first and foremost. Small sigma directions move a little bit. And the gravitational pull pulls them to zero and doesn't let them escape, which is what makes this thing happen. And gravity basically has very little effect here. And so you just get a good fit because they move very fast. Okay? So this fact is super important because what it says is that the actual evolution of gradient descent when run on machine learning problems will move first and foremost in directions that have large singular values. That's where it's going to try to fit. Which comes back to this kind of dimensionality reduction, right? In a way, that it's not just the case that the subspace represented by large singular values is where you're going to fit. It's also that within that nested sequence of subspaces, all of which are relevant, you're going to first fit in those directions which are the biggest singular values. And then you'll fit the next ones, and the next ones, and the next ones. Yeah?
Because like on the right side of the term, if you have like the minus, that would be very small limit, like back to large system value.
You're saying that if this thing is small, it might counteract that. Sure, but when this thing is small, it means you've already fit that direction, right? So you're interested in what happens when you haven't fit it yet. When you haven't fit it yet, this sigma is going to say, move, fit to it, fast. Your eta is going to tell you, hey, go slow, right? That's your learning rate. And the sigma is going to say, no, keep moving, And so you can see also that your eta, the learning rate, is controlled by how big these sigmas are. You can't let any of these dimensions go unstable. It's like intuitions that you get from the math. Okay, so with that, there's two things I want to do. One, I'm going to just do, so let's see. So now I'm going to do two little perspectives. So there's regularization that's explicit, right? Explicit regularization, like I add a ridge term, something like this. But there's also other ways to get regularizing effects. And what I'm telling you already is from what you're seeing here, for example, even if you did not have the ridge term at all, so no more weight decay, you have no weight decay, this effect is still present. Okay, does everyone see this? Gradient descent, just gradient descent, running on squared loss, no regularizer, will soar and try to fit the directions that have large singular values first. The directions that have small singular values, it will creep along. Okay? You see that? So suppose one of those singular values was very tiny, right? Like 0.01. You're afraid that OLS will give you 1 divided by 0.01, a giant number that's not well represented. Do you see that? That's what we're afraid of. But gradient descent will say, okay, I'm going to take teeny tiny steps in that direction. Right? So there's something really big it's trying to get to, and it will converge there eventually if there wasn't a regularizer. But it's going to move very slowly in that direction. Meanwhile, another direction, it'll move very fast. So this is something which is also interesting. So you could have a problem, and if you run gradient descent for 500 steps, you might never see the effect of this threatened blow-up. Like, it'll blow up eventually in 10 million steps. Yeah?
Are you saying that like more steps of gradient descent can build a worse model?
Ah, excellent. Yes. In fact, this is true. More steps of gradient descent can sometimes give you a worse model. And you might think, wait, what? Okay? I started off saying that we're going to try to solve problems by doing optimization. Gradient descent was a way to do optimization, and optimization was the thing we cared about. But now, looking at the details, we say that, wait a minute. By not running that many steps of gradient descent, for example, we can avoid having something bad actually bite us. Okay? And so this is called early stopping. We'll talk more about early stopping later, but I want to mention it here as part of this general story. But the important thing is that your mind should now be, we're trying to expand your mind. Okay? So what it means is that there's many ways to get a regularizing effect. So in that case, you're getting the regularizing effect of saying, I don't want to have these directions that have small singular values explode in my learned weights. But you're getting that effect without ever using an actual regularizer. We're just getting it from gradient descent itself and using it for a small finite number of steps. Now, I will show you 2 more ways to get this kind of effect. Both of which are representatives of things that are very important. Oh, man. Okay. So I'm like running slow. So I'll just give you these. They're in the homework, so you can grind them out. Cool trick 1. Okay? So, one of the ways that you can, that's very, very important in deep learning, is something called data augmentation. So data augmentation says that you have some actual data, and you run the actual data through your optimization to learn something, and you don't get an answer you like. So what you do is instead of using the data you have, you augment it in some way to get it to behave, the end result behaves better. So there's many real world ways of doing data augmentation, but this is the easiest one. So here's the thing. I have a least squares problem. W. Okay? And when I solve it, I get a bad answer, right? I get things blowing up, like OLS. Or you run OLS, and it blows up. I would like to get something smaller. The weights become smaller. How can I do it without actually adding a ridge regularizer? One trick is, I can say, I'll add a bunch of fake data points. So I'll add a bunch of fake data points in which the covariates, the inputs, just look like square root of lambda times the identity. And the output is just a bunch of zeros. So these are all fake points. What all these fake points are doing, intuitively, is they're saying, please set the first parameter to be something close to 0. Please set the second parameter to be something close to 0. Please set the third parameter to be something close to 0. You see how that's what they're doing? So a bunch of fake equations. But exercise for you. You can just use the OLS formula on this problem, which is x transpose. What happens when you take x transpose x here and invert it? You will see answer is the ridge solution. So you can get ridge regularization, the regularizing effect, without adding any explicit regularizer, running the optimization to completion, and instead just having fake data points. This is an example of something which is very, very useful in practice. Okay, what's the other cool trick? Maybe I'll... So this trick is well recognized. The following trick is less well recognized. So how can you discover this trick? First, you can discover this trick by saying, whenever you're thinking about linear problems, think about the SVD. So one thing you know about the SVD is if you take a matrix or take its transpose, it tends to behave the same way vis-a-vis the SVD, right? So this kind of duality. So other trick is, let's add fake features. So I have my problem, x, w, approximately equal to y. I will add a bunch of fake features. So a bunch of fake features where effectively every single data point gets its own feature. You see that? Like every data point gets its own feature. So you're the nth feature, you're the second feature, like so on. If I do this, what'll happen? If I give every data point its own little knob that can be used to tweak it, I can definitely fit y. Do you see that? Even if originally I couldn't. Now I have a wide matrix. A wide matrix times some vector equaling a short thing is always solvable. So now I can solve this. I can solve this, and then I can just take the w that comes out. How do I solve it? I solve it using infinitely many solutions. So I'll pick the min norm solution. Exercise. Again, this is on your homework. Min norm is ridge solution. So this is something, data augmentation is something you will do all the time, explicitly, and you'll know you're doing it in the context of a deep learning problem. Because you'll have to add these fake data points yourself. It's like you'll figure out a way of adding them. Fake features is a perspective that people have only come to understand very recently. In that sometimes when you make your model bigger and bigger, you might think you're doing something very intelligent of adding cool features. But you might just be doing this. Because think about it. All that you care about, this is like a little bit fast. All that you care about here, I put a square root lambda times the identity. All that you need here is this thing behaves in second moment sense like an identity. right? What does that mean? It means these things are approximately orthogonal to each other, or basically orthogonal to each other. But in a high enough dimensional space, random junk will be approximately orthogonal to itself. And that can do it too. So you get regularization by features. Yeah.
Could you explain to the like why having big features and finding a norm solution also regularizes our original solution?
That is a question which has a longer answer than the 4 minutes I have left in lecture. Okay? Right now, I just need you to understand it mathematically. The intuitions for this are, like, there's different levels of intuition. We'll talk about some of it next time, but I want to make sure I get to one more thing. Okay. So, one more thing, last thing. We've talked about this linear model in some detail using the SVD and so on. How does this relate to nonlinear models and the understanding of gradient descent, solving for deep networks and the like? Like, how do you make the connection? So the way you connect to the neural nets is to use the perspective which comes from like, your choice of where you get it from. There's people who've studied analog circuits know this as small signal models for analog circuits, right? A small signal model for analog circuit says, look at an analog circuit and try to understand what it's doing, understand what it does to a small perturbation of something else. Okay, take a very small signal and put it in. How do you understand a small signal model in analog circuits? You take the original model and you linearize it around an operating point. And you see, how does this model behave? The original thing is nonlinear. There's nonlinear circuit elements. But in the neighborhood of a certain point, it's going to behave locally linearly because it has derivatives. Now, from the perspective of neural nets, your complicated neural net model, f theta, right, of input x, is basically, remember, during gradient descent, what you're doing is you're setting theta. You're going to set theta by making small changes to the weights. So the small signal is at the level of the weights. The weights are going to change in small ways. So you can take the entire model and you can think of it this way. F theta plus delta theta is approximately equal to I'll call it F theta naught, F theta naught of x plus the derivative of that function with respect to theta, some big rho, evaluated at theta naught acting on delta theta. See that? Just taking a first order approximation to the function that we're learning. Why is this okay? Because I'm just going to be taking gradient steps. So I'm going to take small steps. So I only care what happens in the neighborhood. If I take this model, then this, namely the derivative of the function with respect to all of my parameters, this is like a generalized linear model. There are a bunch of features, derivative features here. I can evaluate these for all of my data points. And what's going to happen is that we can try to understand what's going to happen in optimization by looking at how this thing behaves linearly. Because this is something where I happen to start. I can take this and just take this linear part, this constant part, that doesn't change as I change delta theta, and just fold it into the y's. It affects residuals, not directions. So what happens is that the singular value decomposition of this object, not the features you see, but their derivatives, the derivative of all the with respect to all the parameters. This guy and its singular values determine the actual directions that your model will want to move in gradient descent. So if this thing has a high singular value in some direction, that's what you're going to try to fit. At least locally, for one step, for a few steps of gradient descent until this thing stops being representative anymore. Then you have to go to a new operating point. So this object turns out to be really interesting. And so in the homework, you have a problem which asks you to work this guy out and compute its singular values and compute the, so just as you have singular vectors, what's a singular vector? A singular vector represents the direction that you would move in, right? So in the same way, the singular vectors corresponding to the derivative of this guy on the training data represent synthetic features that represent the directions you'll move in. You'll move in the direction of that synthetic feature. Those synthetic features can be visualized. And the ones corresponding to large singular values are the directions you're going to fit first. This is the best tool we know right now to understand a little bit about what's called the inductive bias of a neural net, which is what are the directions it'll actually learn in. So you need to understand this. Okay, I'm now out of time by a couple of minutes over, so I will stop. Next time I'll pick up, I'll talk more about it, but this should give you enough to start on the homework on this part. So you should be able to, I can answer more questions about this online in Ed since we didn't get as far as I would have liked. But you guys had good questions, so that's why we didn't get as far as I would have liked. Okay, I have office hours now, but they're not going to be here. They're going to be in 258 Corey because there's another class in here immediately after us.